final example, and in this case, we're given an experimental rate law, which is up here, K observed times the concentration of NO and the concentration of Br2. And we want to figure out from this, we'll look at if we have one step as being fast and the other step as being fast, and see which would be consistent with this experimentally determined rate law. So these are some of the types of problems you have. You're given an experimental rate law and say, tell me which step has to be fast and which has to be slow to have a rate that's consistent with the observed rate. So in this reaction, we have 2NO plus Br2 going to 2NO-Br. So if we write this in the first step, we have NO plus Br2 going to an intermediate NO-Br2 with forward rate constant K1 and reverse rate constant K minus 1. And in the second step, we have the intermediate interacting with another molecule of NO, forming two molecules of NO-Br, our product. So let's consider what the rate of the forward reaction is here. And so that would be, you can yell it out, K1 times, yes, excellent. And for the reverse reaction then, we're going to have our K minus 1 times our intermediate concentration. Now we can look at step 2, where our intermediate is being consumed, and the rate would equal then K2 times the concentration of the intermediate NO-Br2 times the concentration of NO. All right, so we know nothing now about fast or slow steps, so we can write the formation of our product just in terms of this second step. And again, there are two molecules being formed, so we have a 2, and 2 times this rate for this second step, K2 times intermediate times NO. So again, now we have an intermediate that we have to get rid of. We can't have an intermediate in our final expression. But we can't use the equilibrium constant right now because we don't know anything about what are the fast or the slow steps. So we're going to write it the long way with no assumption about fast or slow steps. So to do this, so we have our intermediate, and so we're going to solve for it in terms of products and reactants. So we're going to write about the change in the concentration of that intermediate. So the intermediate's being formed in the first step. So we first write the rate at which it's being formed. So it's being formed here. So that's K1 times NO times the concentration of Br2. So this is how it's being formed. And then we're going to consider how it's being decomposed. And you told me before it gets decomposed in the reverse of the first step. So we have a minus sign because this is a negative change in concentration. It's being decomposed, and it's being decomposed at the rate with a rate constant of K minus 1 times the concentration of that intermediate. And the intermediate's also being consumed, so that's decreasing the concentration of the intermediate, and it's being consumed in this second step. So it's being consumed here with the rate constant of K2 times the intermediate times NO, so that second step. So this is how we write it if we don't know anything about the rate at which, what's slow and what's fast. So this will always work to write things this way. So that's the overall change in the concentration of the intermediate, how it's being formed, decomposed, and consumed. Now we can use the steady state approximation, and you can always use the steady state approximation in these problems, and that says that this net change is going to be equal to 0. So the steady state approximation then lets you set this entire term equal to 0. And sometimes a question you might get is to say what the steady state approximation is. So you should be able to articulate that in words as well as use it on a problem. So now we can set this all equal to 0, and we can solve for our concentration of our intermediate. So rearranging this then, bringing our intermediate terms on one side of the expression, and again, here's the rate at which it's decomposed and consumed being equal to the rate at which it's being formed. And we can pull out our intermediate, so then that's times k minus 1, k2 times NO, and that's equal to the rate at which it's being formed. And so now we can take that, divide by that term, and we get an expression for the concentration of the intermediate in terms of our reactants and our rate constants. So now we need to plug that back in to the original equation that we had. So this is what we solved for, and now we can put it into here. And if you rearrange that, we have the 2, we have the K1, we have the K2, we have an NO here, we have an NO there, so it's squared, Br2 here, and then on the bottom we have K minus 1 plus K2 times NO. Okay, so that's great, but that's not consistent with the experimentally determined rate law. So something has to be fast and something has to be slow. So let's first consider if the first step is slow and the second step is fast, which would mean that the second step is bigger, it's faster. That's K2 times NO would be bigger than K minus 1. So the second step then is faster than this. So now why don't you go ahead and tell me how this simplifies if that is true. All right, let's just take 10 more seconds. Yep. All right, let's look at why. All right, so that's the answer, and let's consider why. So that means if this is much bigger than this term, that cancels out. If that cancels out, what else cancels? K2 also cancels, and what else cancels? 1NO cancels, giving you this expression. And that is consistent with the answer up there. So you could also see that as the K observed. So that's consistent. And let's just first tell me the overall order. 2. And now let's just look at what would have been true if we had done it the other way around. So if we did it the other way around, we'd say that the first step is fast, so that's a lot bigger than this. If this is a lot bigger than that, we cancel out this second term here. Can anything else cancel? No. So we're left with this expression, and that is not consistent with this up here because we have this squared term. So even if you write it as K observed, that's not consistent. And so the overall order for this would have been 3, which is not consistent with the experiment. All right, so now you know everything you need to know to finish problem